All right, let's take a look at today's clicker question. The equilibrium constant K is 10 for the following reaction. The rate constant K1 of the forward reaction is 10 to the fifth, so that means that K1 is right there. And the rate constant K2, we could have done, I suppose, K minus 1, but that's okay, of the reverse reaction would be what? Okay. So, if you recall, we can use detailed balance to answer this question. It's going to be the forward rate divided by the backwards rate. So therefore, we would say 10 equals 10 to the fifth divided by x in order to, then that's our algebraic equation that we're solving for, because we're solving for K2. And so therefore, the answer is clearly 10 to the fourth. And that would satisfy the detailed balance equation. Last topic for today, I want to talk a little bit about drug binding kinetics. This is very closely related to my own research, and so as a result is very interesting to me. And kinetics are very well suited for describing drug binding, as you may expect. So let me draw out the reaction that's occurring here. We're going to call this small molecule I for inhibitor, and then we're going to call this enzyme E, and then it exists in a dynamic equilibrium with the complex E non-covalently bound to I. Though I'm going to use slightly different terms for the rate constants. In the forward direction, we're going to call this K on, and then in the reverse direction, we're going to call this K off. So I know that we're using usually K with a number, but in this case, what you'll almost always see in the literature is K on versus K off. So K on, because it has two reactants, is a second order rate constant. In contrast, since K off has only one reactant, it's a first order rate constant, okay? And if we're going to talk about the forward rate of this reaction, then I'm going to write the following rate law. It's going to be K on times the concentration of E times the concentration of I, and the backward rate is equal to K off times that concentration of the complex, okay? So we're going to consider the situation at equilibrium, which is fairly close to what the body exists at, or at least we make that assumption. The enzyme and inhibitor concentration within the body is probably fairly close to equilibrium. These two are going to be equal to each other, the forward rate and the backward rate. So that means we can set those two equations equal to each other, and we get an equilibrium constant, Kc. And just like the Kc that we saw in chapter 6, we're going to have the the products on top, and then multiply times this unit of concentration, then the concentration of the reactants down below. And this happens to equal K on divided by K off. Sometimes what you'll see in the literature is this Kd quantity. And Kd is just the reciprocal of the equilibrium constant. And this is often called the dissociation constant. And it's going to be K off divided by K on. We can directly relate this equilibrium constant to the free energy of binding. And we kind of saw this at the end of chapter 6. It's negative RT log Kc, equilibrium constant. But another way to put this is this just equals RT log Kd, because we can use the roles of logland to get rid of that negative sign right up there. Now the last thing I want to say about this is K off is a quantity that is very good as a predictor of drug efficacy. So how effective the drug is at inhibiting its target. Why is this? The reason for this is that the K off happens to equal 1 divided by time spent in complex. So the longer the drug spends bound in complex to its target, then the smaller the K off will be. And typically you want drugs to have very long, what are called residence times. So you want drugs to have a small of K off as possible. Why is this? It means low frequency of drug administration. The most effective drugs tend to have a residence time on the order of days or weeks, though it's rather hard to find molecules that bind to their targets with such a long residence time. So then, what are Kc, Kd, and delta G binding good for? Those are also very useful quantities to know because those mainly predict drug specificity. The more negative that delta G of binding, the more likely the drug is only going to attack its particular target and not any other. So see, the thermodynamic quantities give you good specificity, and the kinetic quantities give you good efficacy. Also notice that if you know the K on and the K off, then if you know both the K on and the K off, because of this equation here, then you get the thermodynamics along with it at the same time. So a good medicinal chemist will seek out drugs that have both of these favorable qualities, along with a number of other favorable qualities, like membrane permeability, solubility, toxicity, etc.